Welcome friends. In this module, we discuss more problems on correlation, regression and rank correlation coefficient. We already discussed that to analyze the relation between two variables x and y, we use correlation analysis which determines the degree of relationship between x and y provided the relationship is linear, and regression analysis establish the nature of linear relationship between the variables. A coefficient measure of the degree of correlation between two variables x, y, known as Pearson's coefficient of correlation, is denoted by Rxy, where Rxy equal to Pxy divided by sigma x sigma y, that is equal to 1 by n summation over I from 1 to n xi minus x bar into yi minus y bar divided by square root of 1 by n summation I from 1 to n xi minus x bar whole square into square root of 1 by n summation I from 1 to n yi minus y bar the square. For two random variables x and y, the coefficient of correlation expressed in terms of expectation as Rxy equal to Pxy by sigma sigma y, that is equal to expectation of x into y minus expectation of x into expectation of y divided by square root of expectation of x square minus expectation of x the square into square root of expectation of y square minus expectation of y the square. Problem 1. For two variables x and y, prove that minus 1 less than or equal to Rxy less than or equal to plus 1, where Rxy is the Pearson's coefficient of correlation. Proof. Let x1 y1, x2 y2, etc. xn yn are the observations on x and y. Consider xi minus x bar divided by sigma x and yi minus y bar divided by sigma y, where x bar and y bar are the means and sigma x and sigma y are the standard deviations of x and y respectively. We have xi minus x bar by sigma x plus or minus yi minus y bar divided by sigma y the whole square greater than or equal to 0, because it is the square of a real number. Adding all such terms for I equal to 1, 2, etc. n and dividing by n, we get 1 by n summation over I xi minus x bar by sigma x plus or minus yi minus y bar by sigma y the whole square greater than or equal to 0. On expansion, this implies 1 by n summation over I xi minus x bar whole square by sigma square x plus 1 by n summation over yi minus y bar whole square by sigma square y plus or minus 2 into 1 by n summation over I xi minus x bar by sigma x into yi minus y bar by sigma y greater than or equal to 0. This implies 1 divided by sigma square x into 1 by n summation over I xi minus x bar whole square plus 1 by sigma square y into 1 by n summation over I yi minus y bar whole square plus or minus 2 times 1 by sigma x sigma y into 1 by n summation over I xi minus x bar into yi minus y bar greater than or equal to 0. This gives sigma square x divided by sigma square x plus sigma square y divided by sigma square y plus or minus 2 times covariance of xy divided by sigma x into sigma y greater than or equal to 0. That is 1 plus 1 plus or minus 2 times Pxy divided by sigma x sigma y greater than or equal to 0. This implies 2 plus or minus 2 times Rxy greater than or equal to 0. That is 1 plus or minus Rxy greater than or equal to 0. This gives 1 plus Rxy greater than or equal to 0 or 1 minus Rxy greater than or equal to 0. That is Rxy greater than or equal to minus 1 or Rxy less than or equal to 1. That is minus 1 less than or equal to Rxy less than or equal to plus 1. Problem 2. Prove that a transformation on the variables x and y to u and v in the form u equal to x minus a divided by c and v equal to y minus b divided by d is making no change in the coefficient of correlation between the variables. That is Rxy is same to Ruv. Proof. Let x1 y1, x2 y2, etc. xn yn are the observations on x and y. Then Rxy equal to 1 by n summation over I from 1 to n xi minus x bar into ya minus y bar divided by square root of 1 by n summation over I from 1 to n xi minus x bar whole square into square root of 1 by n summation I from 1 to n ya minus y bar whole square. Let u equal to x minus a by c and v equal to y minus b divided by d. Then Pearson's coefficient of correlation between u and v are u equal to 1 by n summation over I from 1 to n ui minus u bar into vi minus v bar divided by square root of 1 by n summation over I from 1 to n ui minus u bar whole square into square root of 1 by n summation over I from 1 to n vi minus v bar whole square. This implies R u v equal to 1 by n summation over I from 1 to n xi minus a divided by c minus of x bar minus a divided by c into ya minus b divided by d minus of y bar minus b divided by d divided by the square root of 1 by n summation over I from 1 to n xi minus a divided by c minus of x bar minus a by c the whole square into square root of 1 by n summation over I from 1 to n ya minus b divided by d minus of y bar minus b divided by the whole square. This implies R u v equal to 1 by n summation over I from 1 to n xi minus x bar divided by c into ya minus y bar divided by d divided by the square root of 1 by n summation over I from 1 to n xi minus x bar by c the whole square into square root of 1 by n summation over I from 1 to n ya minus y bar divided by d the whole square. This implies R u v equal to 1 divided by c into d into 1 by n summation over I from 1 to n xi minus x bar into ya minus y bar divided by 1 by c into d into square root of 1 by n summation over I from 1 to n xi minus x bar whole square into square root of 1 by n summation over I from 1 to n ya minus y bar the whole square. This implies R u v equal to 1 by c d into p x y divided by 1 by c d into sigma x into sigma y. That is equal to p x y divided by sigma x into sigma y. This implies R u v equal to R x y. Problem 3. From the following information obtain the correlation coefficient n equal to 12, summation over I from 1 to n xi equal to 30, summation over I from 1 to n ya equal to 5, summation over I from 1 to n xi square equal to 670, summation over I from 1 to n ya square equal to 285 and summation over I from 1 to n xi into ya equal to 334. Solution. We have coefficient of correlation Rxy equal to 1 by n summation over I from 1 to n xi ya minus x bar into y bar divided by square root of 1 by n sigma over I from 1 to n xi square minus x bar square into square root of 1 by n sigma over I from 1 to n ya square minus y bar square. Since n equal to 12 and summation over I from 1 to n xi equal to 30, we get x bar equal to 1 by n into summation over I from 1 to n xi, that is equal to 30 divided by 12. Similarly, y bar equal to 1 by n summation over I from 1 to n ya, that is equal to 5 divided by 12. Hence, Rxy equal to 1 by 12 into 334 minus 30 divided by 12 into 5 divided by 12 divided by the square root of 1 by 2 into 670 minus 30 by 12 the square into square root of 1 by 2 into 285 minus 5 by 12 the square, that is equal to 0.78. Problem 4. Find the regression lines and calculate the coefficient of correlation for the following data on x and y. Also predict the value of y corresponds to x equal to 90. X values 65, 66, 67, 67, 68, 69, 70 and 72. The corresponding y values 67, 68, 65, 68, 72, 72, 69 and 71. Solution. The regression lines are ya minus y bar equal to pxy by sigma square x into x minus x bar and x minus x bar equal to pxy by sigma square y into y minus y bar. To find x bar, y bar, pxy, sigma square x and sigma square y, Pxy equal to 1 by n into summation over I from 1 to n xi yi minus x bar into y bar. Sigma square x is equal to 1 by n summation over I from 1 to n xi square minus x bar square, and sigma square y equal to 1 by n into summation over I from 1 to n yi square minus y bar square. In a previous module, while calculating coefficient of correlation for the same data, we calculated x bar equal to 1 by n into sigma xi, that is 1 by 8 into 544, that is 68, y bar equal to 1 by n summation yi, that is 1 by 8 into 552, that is 69, Pxy equal to 1 by n sigma xi yi minus x bar y bar, that is equal to 1 by 8 into 37,560 minus 68 into 69, that is equal to 3. Sigma square x equal to 1 by n sigma xi square minus x bar square, that is equal to 1 by 8 into 37,028 minus 68 square, that is 4.5. Sigma square y equal to 1 by n summation yi square minus y bar square, that is 1 by 8 into 38,132 minus 69 square, that is 5.5. Hence, the regression line y on is y minus y bar, that is Pxy by sigma square x into x minus x bar is y minus 69 equal to 3 divided by 4.5 into x minus 68. This implies 3x minus 4.5 into y plus 106.5 equal to 0. The regression line x on y, x minus x bar equal to Pxy by sigma square y into y minus y bar, that is x minus 68 equal to 3 divided by 5.5 into y minus 69. This implies 5.5 into x minus 3y minus 167 equal to 0. We can use the regression line y on x to predict the value of y for x equal to 90. The regression equation y on x is y minus 69 equal to 3 divided by 4.5 into x minus 68. For x equal to 90, y minus 69 equal to 3 divided by 4.5 into 90 minus 68. This implies y equal to 3 divided by 4.5 into 90 minus 68 plus 69. This implies y equal to 83.67. While calculating coefficient of correlation between x and y, we can reduce the calculation burden by transforming x and y to appropriate u and v. For example, u equal to x minus a and v equal to y minus b, and we can find the correlation for such u and v values. As per the theorem of invariance of correlation coefficient under linear transformation, the correlation between u and v will be same to the correlation between x and y. For an illustration to solve the problem in such a method, see the following. Problem 5. Calculate Carl Pearson's coefficient of correlation for the following data: x values 10, 12, 13, 16, 17, 20 and 25. The corresponding y values 19, 22, 26, 27, 29, 33 and 37. Solution. Coefficient of correlation are equal to covariance of xy divided by standard deviation of x into standard deviation of y. The problem can be solved by simply following the steps shown in above example, but for some computational easiness, the problem can also be solved as in the following illustration. We have the result that correlation coefficient is independent of change of origin and scale. Hence, we can calculate the correlation between x and y by altering x and y by some linear transformation. Here, consider u equal to x minus 16 and v equal to y minus 27. The correlation between u and v is same to correlation between x and y. Correlation between u and v are equal to covariance of uv divided by standard deviation of u into standard deviation of v. The calculations are x values 10, 12, 13, 16, 17, 20 and 25. The corresponding y values 19, 22, 26, 27, 29, 33 and 37. U values are x minus 16, they are minus 6, minus 4, minus 3, 0, 1, 4 and 9. The corresponding v values, y minus 27 values, they are minus 8, minus 5, minus 1, 0, 2, 6 and 10. Now, the u square values are 36, 16, 9, 0, 1, 16 and 81, and sigma u square equal to 159. V square values 64, 25, 1, 0, 4, 36 and 100. Their sum is 230. U into V values are 48, 20, 3, 0, 2, 24 and 90. Their sum 187. Sigma u equal to 1 and sigma v equal to 4. Covariance of uv equal to 1 by n into summation u into v minus u bar into v bar, that is 1 by 7 into 187 minus 1 by 7 into 4 by 7, that is 26.71 minus 0.082, that is 26.628. Variance of u, that is 1 by n into summation u square minus u bar square, that is 1 by 7 into 159 minus 1 by 7 the square, that is 22.71 minus 0.02, that is 22.69. Variance of v equal to 1 by n summation v square minus v bar square, that is 1 by 7 into 230 minus 4 by 7 the square, that is 32.86 minus 0.327, that is 32.533. Now, correlation between u and v are equal to 26.628 divided by square root of 22.69 into square root of 32.533, that is 0.98. That is correlation coefficient of x and y equal to 0.98. Problem 6. X and y are jointly distributed with the coefficient of correlation 0.40. Standard deviation of x equal to 3, standard deviation of y equal to 4. Find variance of 3x minus 2y plus 4. Solution. Variance of 3x minus 2y plus 4 equal to 9 into variance of x plus 4 into variance of y minus 12 into covariance between x, y. We have the coefficient of correlation between x and y. This implies 0.4 equal to covariance of x, y divided by 3 into 4. This implies covariance of x, y equal to 12 into 0.4, that is equal to 4.8. Thus, variance of 3x minus 2y plus 4 equal to 9 into 9 plus 4 into 16 minus 12 into 4.8, that is 87.4. Rank correlation coefficient. When we are considering two characteristics which are quantitative in nature, and if it required to find the coefficient of correlation between them, we are rely on Pearson's coefficient of correlation using the paired observations on x and y. But if the characteristics under consideration are qualitative in nature, they are not possible to measure numerically. For example, consider the characteristics of the ability in drawing, let it be x, and the ability in music, let it be y. It is not possible to measure numerically the values of x and y for an individual. But if there are n individuals, it is possible to rank these n individuals according to the ability in drawing x and according to their ability in music y. If these two characteristics are having the positive correlation, then ranks obtained for the individuals based on x and y will be in the same order. If these two characteristics are having high negative correlation, then ranks obtained for the individuals based on x and y will be in reverse order. Using the ranks obtained for the n individuals based on the characteristics x and y, a method of finding the coefficient of correlation is derived by C. Spearman in 1904. The coefficient of correlation for two characteristics which are calculated based on the ranks is known as Spearman's rank correlation coefficient. Let there be n individuals ranked according to two qualitative characteristics considered. Let xi yi denote the rank of the ith individual when ranked according to the characteristics. So, the xi yi values are the numbers from 1 to n. Since xi values are the numbers from 1 to n, the mean of x values x bar equal to sum of the first n natural numbers divided by n, that is 1 by n into n plus 1 by 2, that is n plus 1 by 2. Similarly, y bar equal to sum of first n natural numbers by n, that is 1 by n into n plus 1 by 2, that is n plus 1 by 2. Variance of xi values sigma square x is equal to sum of squares of first n natural numbers by n minus of n plus 1 by 2 all square. This implies sigma square x is equal to 1 by n into n plus 1 into 2n plus 1 divided by 6 minus of n plus 1 by 2 the whole square, that is equal to n square minus 1 divided by 12. Similarly, sigma square y equal to n square minus 1 by 12. Let di equal to xi minus yi. This gives d bar equal to x bar minus y bar, that is equal to 0. Variance of d values sigma square d equal to 1 by n sigma di square minus d bar square, that is 1 by n sigma xi minus yi all square minus 0 square, that is 1 by n into summation xi minus yi the whole square, that is 1 by n into summation over I from 1 to n di square. Since x bar equal to y bar, we can rewrite 1 by n summation over I from 1 to n di square as 1 by n summation over I from 1 to n di square, that is equal to 1 by n into summation over I from 1 to n xi minus x bar plus y bar minus yi the whole square. This implies 1 by n into summation over I from 1 to n di square equal to 1 by n into summation I from 1 to n xi minus x bar minus of yi minus y bar the whole square. This implies 1 by n sigma over I from 1 to n di square is equal to 1 by n into summation over I from 1 to n xi minus s bar whole square plus 1 by n into summation I from 1 to n yi minus y bar whole square minus 2 times 1 by n into summation over I from 1 to n xi minus s bar into yi minus y bar. This implies 1 by n into summation over I from 1 to n di square is equal to sigma square x plus sigma square y minus 2 times covariance between x and y. But we have covariance between x and y equal to r into sigma x into sigma y, where r is the coefficient of correlation. Hence, 1 by n into summation over I from 1 to n di square equal to sigma square x plus sigma square y minus 2 r into sigma x into sigma y. Since sigma square x equal to sigma square y equal to n square minus 1 divided by 12, we get 1 by n into summation over I from 1 to n di square equal to n square minus 1 by 12 plus n square minus 1 by 12 minus 2r into square root of n square minus 1 by 12 into square root of n square minus 1 by 12. This implies 1 by n into summation over I from 1 to n di square equal to 2 times n square minus 1 by 12 minus 2 times r into n square minus 1 by 12. This implies 1 by n into summation over I from 1 to n di square equal to 1 minus r into n square minus 1 divided by 6. This implies 1 minus r equal to 6 into sigma over I from 1 to n di square divided by n into n square minus 1, or the coefficient of correlation r equal to 1 minus 6 into summation over I from 1 to n di square by n into n square minus 1. Problem. The following are the ranks given by 2 judges for a competitor in a music competition. Are they like the same type of music? The ranks given by judge 1, 5, 4, 2, 6, 7, 10, 9, 1, 8 and 3. The ranks for these competitors given by the judge 2, 4, 1, 5, 7, 8, 9, 7, 6, 3 and 2. Solution. To find the correlation coefficient based on the ranks given by the judges, to find the relation of their liking to the same type of music. The calculation for finding Spearman's coefficient of rank correlation is as follows. Xi values are here, yi values are here, di values are xi minus yi values, and to find di square values, they are xi values are 5, 4, 2, 6, 7, 10, 9, 1, 8 and 3. The corresponding yi values are 4, 1, 5, 7, 8, 9, 7, 6, 3 and 2, and the DI values are 1, 3, -3, -1, -1, 1, 2, -5, 5 and 1. The DI square values 1, 9, 9, 1, 1, 1, 4, 25, 25 and 1. Finally, sigma DI square equal to 77. Hence, R equal to 1 minus 6 into sigma over I from 1 to n DI square by n into n square minus 1, that is equal to 1 minus 6 into 77 divided by 10 into 10 square minus 1, that is equal to 1 minus 462 divided by 990, that is 0.533. Since correlation is positive, the judges are almost like the same type of music. Now, let us have a quick look at what we have discussed in this session. More problems on correlation and regression analysis are considered in this module. The concept of rank correlation coefficient is also introduced. Solved problems will help the viewers to improve the level of understanding the ideas discussed. Before we move to the next session, please try to answer the following questions. A. X and Y are two random variables with the mean 6 and 12, standard deviations 3 and 4 respectively. Find the coefficient of correlation between u and v where u equal to 4x minus 5y and v equal to 2x plus 3y. B. Two regression equations obtained from a given data are 3x plus y equal to 10 and 3x plus 4y equal to 12. Obtain 1 x bar and y bar, 2 rxy. C. For two random variables x and y with the same variances, prove that correlation between x and x minus y is square root of 1 minus r by 2, where r is the correlation coefficient between x and y. D. Obtain the rank correlation coefficient for the following data: x values 15, 22, 28, 12, 40, 60, 20 and 80, corresponding y values 40, 36, 50, 34, 20, 10, 28 and 60. The books for your reference are Introduction to Probability Models, Sheldon M. Ross, Academic Press, 1997. Introduction to Mathematical Statistics, S. C. Gupta, V. K. Kapoor, Sultan Chand and Sons, 2003. A First Course in Probability, T. K. Chandra, D. Chatterjee, Narosa, 2003. A First Course in Probability, Sheldon M. Ross, Pearson Education, 2007. Probability and Statistics for Engineers, R. A. Johnson, PHI, 2005. Hope you enjoyed this session. See you next time. Until then, goodbye.